Thanks everybody for coming, particularly to the people in the actual audience for attending the show, and for people who are watching the live stream. Thank you for watching as well, and perhaps in the future when this gets posted, thank you again for watching. Okay, so this talk, today there are two talks. This talk is, I guess you would consider the more basic of the two. The next one is on the matrix, which can be a little bit overwhelming for some people. So I hope this one is a little easier to understand. Okay, so let me get started. So first things, if you've seen my talks before, you'll know that I've always put these two caveats. I am not an engineer by training. So what you see here is based on experience from what I've read and what I understand. And a lot of my experience is Williams-based. It can be applied to both Gottlieb and Bally's solid states. It could probably even be applied to Stearns and modern machines. But in essence, most of my experience is Williams. So what you will see is Williams-centric. My advice to you is look at the manual. Based on what you see here, you should be able to apply what's here into for any machine as long as the information is in the manual. One caveat with manuals, they're mostly correct. There are printing errors or copy and paste errors, so ultimately you still have to do some diligence. Don't always trust the manual. So today there are a whole bunch of different subtopics in this area. Electrical fundamentals, some of you may already know a lot of this. Wiring diagrams, I see a lot of times people asking, how do I wire this, what's connected where? A wiring diagram typically has all the answers, and it's really important, in my opinion, to learn how to read one, because often you can find the answers right there. You don't need to ask somebody, hey, can you post me a photo of what this looks like? Source to consumer, that is a subtopic from how the power is generated from the grid and it ends up in your home. Transformation, that covers how the power enters from your home and gets transformed within the machine. Transformer to board is outputs from the transformer to the boards, and there are all sorts of different voltage levels, as you'll see. System consumption is how the machine actually uses that electrical power. Circuit operation will be how some of it is actually processed. Problems with operation, what goes wrong, common scenarios, not uncommon ones, and then we'll finish with a summary. And as Chase said, please hold all questions until the end. Okay, so this will be very fundamental if you did high school physics like I did, which is the extent of my experience. You probably would have been taught these fundamental electrical concepts: voltage, current, and resistance. Excuse me. The key with voltage is, so voltage is a potential difference between 2 points, and the biggest thing to know that it is relative. Everything you will encounter in real life is relative. There is a point of reference and a point of measurement. And this is true with almost everything. The only thing I can think of that's scientific, that's absolute, is absolute zero. Everything else is relative. AC versus DC, this is the direction of the current flow. Direct, alternate current, or direct current. Direct current always flows in one direction, from the high potential to the low potential. Alternating current always flows will flow back and forth between 2 points. The other thing about alternating current, because it flows back and forth, it is a sine wave. Direct current is a line. It is a single point, or single group of points, a line. How to measure. So the other thing about measuring is that people often confuse is measuring incorrectly. You cannot set your DMM to VAC measurements and try and read VDC if you're trying to measure VDC. What the DMM will tell you is what VAC is, and vice versa. And those funny little symbols on your DMM, the V with a squiggly line over it or the V with the bar over it, tells you exactly what the meter is set to. The wavy line is the sine wave, which is AC. The straight line is for DC. So what is current? Current is simply a charge flow. It's positive or negative flowing to the other positive or negative terminal. That's all it is. The interesting side effect of current flow is you generate a magnetic field. And that's actually taken advantage of in your machine because it effectively converts electrical energy into current, which generates a magnetic field, which pulls a metal plunger into a solenoid, which generates mechanical energy or kinetic energy. Resistance, this is difficulty of flow. You can think of it like friction. The higher the frictional surface, the more the resistance to flow. It's the same thing. Some people use the pipe analogy, narrow pipe, it's more difficult for water to flow through a narrow pipe than it is a wide pipe. So I don't think I put a note here on it. Okay, so before I move on to the next slide, and some of you may have heard this before, to help you understand potential difference, I use what I call the building analogy. And a great example of it is right here. You're sitting in a building here on level 5. And if you go down to the street, to the very lowest level where the courtyard Marriott is, that's level 1. And yet, if you look at the entrance behind me, there is a level 3 entrance. So you may ask yourself the question, well, what's ground level? Ground level is whichever level you entered on. It could be 5, it could be 3, it could be 1. And this is what I'm trying to emphasize about the point of reference. Most people think of ground as a reference, but it depends where your ground is. If you came in through the loading docks, your ground is the level 5 where you are right now, and anything below that level is a negative. If you came in at the bottom level where the trolley runs, you came in at level 1, and everything above that is positive. And if you came in through the main entrance, on which I guess you call it the main entrance, on level 3, which is a very popular one, then you're sitting right in the middle, and everything above that, levels 4 and 5, are positive, and everything below that is negative, levels 1 and 2. And this is the importance of ground. It's always the black lead, typically. It's the black lead on your DMM. And people think, oh, ground is always 0. Well, ground is usually 0. It's not always 0. Again, depends what floor you come into the building as to where your 0 point is. The thing the reason why I like to use the building analogy is because charge always flows from the higher potential to the lower potential, which means that it will always go from floor 5 to floor 4 to floor 3 to 2 to 1, regardless of whether you're calling floor 5 0 or not. So it'll always go from floor 0 to floor -1 to floor -2. It always goes in that direction. And this is the reason why it's important to know what's relative. So if you have trouble understanding what voltage is, negative, positive, try and think of it in terms of a building, sitting on a side of a hill, and where you enter, what your street level is. So the relationship between these, Ohm's law. Yes, you did high school physics. Somebody probably wrote that on a board, V equals IR. It's exactly what it means. Voltage is current multiplied by resistance. One of the big things to take away from this is because the V and the I are on either side of the equal sign, they are proportional to each other, which means if you double the voltage, you double the current. So if a circuit is rated for 5 volts and you put 10 volts in it, you put 10 volts across it, I should say, you actually double the current that will flow through it. And this is why a lot of things basically, when you put 110, your line voltage across it, and something is rated to run at 5 volts, you've basically put 20 times the amount of voltage across it, and you'll fry the components pretty quickly. Another relationship as part of this, which is often overlooked, and I've done this in the past, is power dissipation. How fast does that energy, when it flows in form of electricity, how fast does it actually generate heat? How quickly does it dissipate it? And the relationship between that is power is voltage times current. And if you substitute current with voltage and resistance, you actually also get power is voltage squared divide resistance. These are important relationships to understand, because if you're trying to design a circuit and you don't account for the amount of power you've actually dissipated, and you put in a 1/4 watt resistor and you dissipate 1/2 watt, that resistor will slowly cook. If you put 5 watts of power across a 1/4 watt resistor, that won't cook, that will fry. And you'll end up with black carbon all over the board very quickly. And this is why the power rating is important. A lot of people don't consider it. They just consider what's the voltage and what's the current and what's the resistance. It's important to choose the appropriate power rating. So wiring diagrams, and I'll have some examples of this following in the following slides. A wiring diagram shows how components are related to each other. The key to understand here is it is a logical representation. It is not what you see physically wired in the machine. It's telling you how the wires should be connected, not necessarily how they are connected physically. Another thing that people often confuse is schematics and wiring diagrams. They're similar, they're not quite the same. Wiring diagrams typically are strictly for things like how your cabinet is wired. This red-white wire goes to this point, connects to that point. A schematic typically involves a logic circuit with integrated circuits and chips with multiple gates and stuff like that. You don't see those in cabinet wiring because they live on boards. But anyway, I'm just being a little pedantic here, but it's important. They do often share the same symbols, so that if you learn how to read a wiring diagram, you can probably look at a schematic and say, oh, well, that makes sense. And just for another personal experience thing, learning how to read a wiring diagram is really helpful, because the other day my water heater died, and I opened it up and I looked at it, and there behind the panel was a wiring diagram. It told me exactly how it was wired. And I looked at the wiring and it's like, oh, this makes sense, and this is where it was right or wrong. So again, this is just a simple thing that you can learn that can help you. So the key with the wiring diagram, points connected on a wiring diagram are electrically continuous. That means anything that's connected, regardless of what order it is, it's all continuous electrically. You can set your DMM to continuity, and every point that it's connected will read continuity. Junctions, dots, again, you'll see this I'll show you in the coming diagrams. The dots are basically points that are also connected, but it allows you to say explicitly this line and these lines are all electrically on the same connection. Electron flow is not linear, and what this means is that it flows everywhere. If you have a wire that's connected at points 1, 2, 3, 4, the electrons don't flow in the order of 1, 2, 3, 4. They're pretty much everywhere instantaneously. Now, it's not instantaneous as in 0 seconds. There is some speed to which the electrons move, but it's so quick that you can consider it instantaneous. So this is a cabinet wiring diagram from a System 11 machine. And you can actually see it's probably a little bit small, but essentially what it's showing you is all those lines show you what's connected to where, and they've even done the nice thing and put wire colors in there. And again, you can look at it, and I actually have a sample up here, and you can come and look at this later to see that I'm really telling you what's in the manual is represented here. The wire colors are really, really important, and they're almost all documented. Another interesting thing about this wiring diagram is it shows you what's on a board logically, not the actual components, what's on another board logically, what comes out of the board, and where it goes to. This information is all here. It just looks really difficult to read, but again, like I said, if you learn how to read one, you will not be asking people, please post me a photo of what this is supposed to look like, because more often than not, it's actually documented. This little piece down here at the corner, this is a flipper wiring diagram. This tells you exactly how the flippers are wired. And again, if you learn how to read that, you can go to your machine and you'll say, this actually is what's there. And I can't remember if yep, there I did. So this is the flipper wiring diagram blown up. And what you'll see represented here is where the voltage comes out, the colors of the wires, what are connected through connectors and pins. This is the actual solenoid itself. There's 2 windings. That's what a winding looks like. These are diodes, and if you look on your flipper diodes, particularly parallel wound diodes, you'll see that there are 2 diodes, and they're often placed between terminals 1 and 2 and 2 and 3. And again, this is shown here. Then it comes back out, it goes through the flipper switch. This is actually in your cabinet. and it comes back to the board and it goes to ground through the flipper relay. The thing with the flipper wiring with the wiring diagram in general is it will show you the wiring across multiple components. Sometimes you will not see the wiring. The wiring is actually on the board. You have to remember, a printed circuit board is nothing but a bunch of wires. They're just copper traces on a board, but they're still wires. Here's the Fliptronic wiring diagram, and it's actually very much the same. There's rectification, fuse, wire with colors, solenoid, same thing, 2 diodes, and a return. In the case of a Fliptronic flipper, it's actually under software control. So software will control the ground. In the case of a System 11, there's no software control in this. You press the button, ground. When that happens, the flipper flips. No, software is not involved. Here, with Fliptronic, software has to actually ground the transistor in order for it to energize. And that's why you don't see any of that ground connection here. That's on the board in the schematic. So now we're going to switch from all of those wiring diagrams to understanding the bigger picture, like how does that power actually get from the company, the power company, to your door, through your machine, and get distributed throughout it. Electrical power transmission, it comes from the grid. Someplace it's generated. It's typically generated by a turbine through electromagnetic induction. So, as I said earlier, when current flows, a magnetic field is generated. Well, equally so, if you move a magnet, if you move a magnet and change a magnetic field, you'll generate current. It's the exact reverse. I think it's Faraday's law, electromagnetic induction. So typically that is done by things like hydroelectric, or it could also be done by burning coal to produce steam, which turns a turbine. It could also be done using nuclear, which basically heats up water, which produces steam that turns a turbine. In fact, even in your car this is done. If you're familiar with an alternator in your car, it's the same principle. The engine turns the alternator, which generates current, which charges your battery as you drive. It's everywhere. The difference here is that when the electricity is generated at the source, typically hydroelectric, they raise the voltage to a really high voltage level, 500 kilovolts. You may ask yourself, well, why would you do that? If you go back to Ohm's law, V equals IR. If you raise the resistance, if you raise the voltage and you still have the same current transmission, you'll lower the resistance. It's part of the way they do this. It's just basically to reduce the resistance, because every time there is resistance, there's friction. Friction dissipates energy as heat. That's lost. That's the only typical reason. But the problem is that, well, you can't go around putting 500 kilovolts into people's houses. So then they have what they call substations, which transform the voltage back down towards the lower end, 10 kilowatts, even that's quite high. And then they go further down to street distribution. And if you actually look on the streets of your homes, you'll see these little gray cylinders on power poles. Those are actually transformers that transform the substation voltage down to a level that you can consume in your home. And it's typically about 230 volts here in the US. But as I mentioned here, line voltage differs between country. And typically in Japan, it's 100 volts. So if you look in your manual, you'll see that there's a selection for a 100-volt configuration. Sometimes people import those machines and they're still configured for 100 volts, which is not good. It will work in 115 US, but it may not produce your desired results. You really should have 115. There'll be a configuration for that. And then EU, Australia, and New Zealand is 230, 240. A big takeaway message here is please do the right conversion and don't cut the wires. Often you'll see a lot of these machines have been operated in the past, and some operator has decided to cut the wires instead of move the jumpers around. Use the jumpers, don't cut the wires. So this is the diagram that tells you how the transformer is wired and what the selections are, and it's kind of complicated, so I don't want to go into it too much, but at least the transformer selections. But what I do want to do is discuss the line voltage. The 3 prongs are your hot, neutral, and ground wires that come into your machine. They typically go through a line filter, and this is from a later WPC machine. Williams did change between early and late, but the elements of the components are still the same. The order in which they did it is different. So the line filter might be placed further on, after the switch, before the switch. Again, consult the wiring diagram, but the principle is still the same. There is a line filter, there is a service outlet, and the service outlet is always placed before the switch. Otherwise, you'd have to turn the switch on for the service outlet to work. This is the switch, this is a fuse, this is a thermistor, and on earlier WPCs, there's also a varistor which runs across the hot and neutral. And that varistor is typically there to prevent things like lightning strikes from taking out your machine. And then the whole bunch of wires here, this is all to do with voltage configuration. And pretty sure I don't discuss that because it is documented and it can be confusing. I didn't want it to go beyond it to get too confusing in the scope of this talk. So, what is a transformer? A transformer uses electromagnetic induction to do this, and this is a changing magnetic field. What happens is that when the water turns the turbine, typically, in a hydroelectric case, there is a magnet, and the magnet runs through a wire, and when it does that, it generates a current. But because it's turning in a circle, it actually always, the poles, I guess, of the magnet rotate between north and south and back and forth. And when that happens, you generate current that flows one way, then backwards, forward, then backward, forward, then backward. And that is the essence of alternating current. Direct current always flows in one direction. For arbitrary sake, we'll just call it forward. Alternating current goes forward and backward, and that's the nature of the turbine. The nice part about this is that the ratio of the number of windings will control how much the voltage is either raised or lowered. Before I get into that, the winding, a transformer is basically a winding around a magnetic core. Again, it's that same thing. The wire is wound around something, and when the current changes, there's a magnetic field, or when a magnet moves, there is current generated. The ratio is the thing that's important here. If I have one winding of wire on the input side and one winding of wire on the output side, then I get equal voltage. If I have one winding of wire on one side and double the winding on the other, and I can't remember for the life of me off the top of my head whether it's half or double, but you understand, it's the ratio. If you put 4 times the winding, you get a quarter or 4 times the voltage. That is the key, and all of these are specifically calculated numbers if you buy a transformer. Transformers, transformers typically have commercially produced transformers typically have a dual or single winding from the primary side, that's the input, and those are typically 115 or 230 because those are the very common line voltages. And on the output, depending on the transformer you buy, most commercial transformers have a single output, i.e. they have a fixed ratio of 115 to 50 volts or 24 volts or 12 volts, whatever it is that the output purpose is. The thing with these transformers in pinball machines is that they have multiple windings on the output side because there are different levels of voltage that are required. Solenoids run on high voltage, 50 volts. Flashes run on intermediate voltage, 20 volts. And power runs on lower voltage, 12 volts. And digital logic runs on an even lower voltage of 5 volts. So there's multiple windings on the output side, but there's only typically one, actually there are 2 in this case, 2 windings on the input side, 115 or 230. In the case of Williams transformers, there's actually a third option for that Japan 100 volts. And if you read the manual, they refer to that as low line voltage. So sometimes you'll see someone says it's configured for low line. What they mean there is it's configured for like 100 volts instead of 115. If you put 115 volts, but it's set for 100, you are putting a ratio of 1.15 voltage over what's expected. So if the output is 50 volts, your output will be 50 times 1.15. And I don't know what that number is, but you can run through a calculator. That's the bottom line here. Again, if you take a transformer that's configured for 110 and you bring it to Europe and you shoot 230 through it, you'll get double the output. So what would come out as 50 volts in the US comes out as 100 volts in Europe. And that will probably fry a lot of things very quickly. Fortunately for people in the US, that's actually to their benefit, because if you re-import a machine from Europe and it's configured for 230 and you only put 115 through that, you'll actually only get half of the voltage. So what would be 50 volts on the output side ends up being 25. So your solenoids will feel really weak if they work at all. Do not confuse a regulator for a transformer. They are different. A transformer uses AC to move voltage levels up and down. A regulator uses circuitry to control DC voltage, not AC voltage. So do not use those terms interchangeably. This is a transformer wiring diagram. You'll always see that curvy representation. Those are the transformer windings, just like a solenoid or a coil in your machine. It is nothing but a bunch of wire wound around something. It's exactly the same thing. These are the two transformer windings on a Williams transformer. In essence, you only need one winding for 110. You need both of these windings for 230, and I should say 115, so I'm sorry, it's 115 versus 230, because essentially it's a ratio of 1 to 2. This shows the wiring, this shows the actual bundle of wires as they're wired, and you can see all those wire colors there. Those wire colors actually are representative of this in this wiring harness. The colors in the diagram will match what's in this harness. And I've actually blown it up here. I think it's, so you can see these colors here. And each of these colors represents a different output winding at a different voltage level used for a different purpose. The black yellow is 50 volts for solenoid. The white red is 20 volts for flashes. The blue white is 18 volts for lamp. The red is, I think it's 9.8 or 10 volts for digital logic, and the voltage output here is on this side. And then there's the white-green, which is used for power. The thing also to remember is the numbers quoted here are generally referred to what is called a nominal voltage. If you put your DMM leads across and do the measurement, it may not read exactly 51.4 VAC. The reason why is your line voltage coming into your house varies. And if the line voltage varies, the output side is going to vary in accordance. So it's a rough range. Don't say it has to be exactly 51.4. Okay, so this is transformer to board. This transformer secondary output, this big bundle of wires here, carries all of the power that goes to be used for different purposes. And in a Williams machine, they are used for digital logic, the 5-volt line, digital power, the 12-volt line, lamps, general illumination, matrix, and flashes. And the interesting thing with lamps here is that I've broken them down into those 3 separate groups because those 3 groups are powered from different sources. The general illumination is 6.3 volts AC. The lamp matrix is 18 volts DC, and flashes are 20 volts DC. So when you're referring to a lamp, you really need to know what kind of a lamp it is, and by virtue of what kind of a lamp it is, where the power source is. Not all lamps are the same in a machine, as you've probably already realized. General illumination is always on. It can be dimmed in WPC machines. Lamp matrix is software controlled, typically presented in an 8x8 matrix, individually controlled by software. And flashes are individual lamps that go off at certain events controlled by the software at a one-time thing rather than in a matrix. The 51.4 volt VAC winding is for solenoids. One thing I didn't actually discuss here in the slides is that what you see as VAC after it's rectified is not the same as VDC. So you'll often hear people say, oh, go measure the solenoid line, it should read about 50 volts. Someone goes to measure it and it reads 70 volts. And they say, is it too high? And the answer is no, because it's actually 50 volts AC nominal. And when you rectify that, convert it to DC, it actually you end up multiplying it by roughly by the square root of 2, 1.414. And if you do 50 times 1.414, you'll end up at about 70. And that's the nature of the sine wave. AC is a sine wave. The voltage is not fixed at any one point. It moves up and down in the pattern of a sine wave. And all your DMM is trying to do when it reads a VAC is do an average. I think the correct terminology is root mean square, but again, I'm not an engineer. I just read this stuff and sometimes it goes over my head too. The audio tap is an interesting thing. It features what's called a center tap. You'll sometimes see this written as VCT. On this diagram here, you can see that the black wire shows one winding, and then there's a brown wire that taps off the center, and then there's another winding that goes to the end, and that's orange. This brown wire here is the center tap. And I'm pretty sure I don't talk about this because, again, it's a little bit beyond it, but essentially a center tap is used to generate negative voltages. So you'll see in the system sometimes the sound part of it has 12 volts and minus 12 volts. In order to generate the minus 12 volt, they use a center tap, and they ground reference the center tap as 0. So this, for argument's sake, in this example, the black wire would be 12, the brown wire would be 0, and the orange wire would be minus 12. Again, depends where you put that ground reference, because if we tie the orange wire to 0, the brown wire is going to be 12, and the black wire is going to be 24. So you then may ask yourself, well, why would you want negative? What's the purpose? Why don't you just stay positive? You know, always use absolute values, 0, 12, 24, minus 12, 0, 12. Who cares? What's the difference? The difference is when you start dealing with larger potentials, you start dealing with larger potentials to cause damage. So the difference between 0 and minus 12 is only 12 volts. Sure, it's negative 12, but I mean, in absolute value terms, it's 12 volts. The difference between 0 and 12 is 12 volts. Now, if I put the 0 reference point at 0 and I'm trying to run a sound system and the whole difference is 24 volts, well, now the difference between ground and the highest value is 24 volts. And if I do something incorrect with that, I could shoot 24 volts instead of 12 volts and fry something. And that's part of the reason why. It keeps the numbers a little bit lower. It makes it a little bit harder for people like me who aren't really good at analog to look at things and say, why would you do this? But that is my understanding of why it's done. The center tap is the key. You ground the center winding, you tie the center winding to ground and cause one of the windings to go on the negative side and the other winding to go positive. This is why I can't emphasize it enough. The reference point is what matters. The display, plasma, that's typically high voltage. I don't want to touch that. I do not use high voltage on my bench. It's way too dangerous. Another interesting point with the later WPC and WPC 95 and 89 machines is that they have what's called an interlock switch. Williams started introducing this at about halfway through the Twilight Zone run, I believe it is. So some Twilight Zones have it, some Twilight Zones do not. All machines before it do not. Adams Family does not. But Adams Family is an interesting exception because Adams Family Gold was produced after Twilight Zone. So Adams Family Gold machines have an interlock. Adams Family machines do not. Which is also interesting because if you put an Adams Family Gold ROM in an Adams Family, it will tell you that the coin door is open and you're interrupting high voltage, but there is no switch, because the software was written for a machine in which it had a physical switch. You can also see that on this diagram right here. These two wires that run off, they go down to the interlock switch. Oops. They go down to the interlock switch. And this, I believe, is from a Twilight Zone, which is why you don't see the interlock switch. The interlock switch is a momentary double throw switch. Momentary means you have to push it in order for it to actually engage. Some of the later WPC machines actually have a switch where you can pull it out. If you pull it out, it will lock the switch on. And you can usually tell it's the earlier switches are just a flat surface that's conical. The later machines have a kind of a dip in it. You'll see. You'll understand it. If you can pull it out and it holds, you have an interlock switch that will hold in the on position. That's a neat little trick that some people don't know. You can actually pull it out. This is more of the same. This, I believe, yeah, so this is for the center tap. You can see here, one winding, center winding, other winding. That's what the center tap will look like when you see it. This is just a straight, simple winding of high voltage. This is the center tap for the audio. So once it reaches the board, what happens? The digital logic side in the lamp matrix uses J101, takes these two, and it's the 18-volt line and the 5-volt line. J102 is the high volt line, it's the flasher 20-volt and the solenoid 50-volt. J112 is the digital power, that's the 12-volt power line, not the 12-volt digital line. I don't want to get into that too much here. There are two 12 volts on the machine. One is regulated, one isn't. Do not confuse them. General illumination, 6.3 volts. Audio, one winding, center tap. Excuse me. Display, two windings. The 80 volts and the 100 volts shown here. 80 volts, 100 volts. This you'll often see at the back of a WPC manual. It just tells you what color wires go where and how they're connected. In most manuals for each game, they are mostly correct. There are errors. Very few, but there are errors. In this case, you can see here the red wires are the digital logic, the blue-white wires are the lamps, the white-red wires are the flashes, 16 VAC, roughly about 20 volts DC, and the black-yellow, and you can see here even this is wrong. That's not 16 VAC, it's 51.4. So that's an error right there. On the other side, this is the other transformer secondary, the white-green wires. It's 9-point VAC, produces 12-volt power. This powers things like motors, optos, those sorts of things. So what happens when it hits the board? Well, AC is pretty much useless to any application that's anything digital. It has to be DC. And the reason why is the digital logic operates on 0 volts DC equals 0, logical 0, or low, and 5 volts DC in the TTL world means 1 or high. AC would constantly move back and forth between 0 and 5, 0 and 5, and you get no logic whatsoever. So everything has to be converted, and that's called rectification, AC to DC. Rectification can be half wave or full wave. So a sine wave, if you're familiar with it, it goes up, it goes down, it goes up, it goes down, positive, negative, positive, negative. If you rectify that on the positive side only, you'll get the positive side of the wave rectified, the negative side of the wave is completely ignored, so there's nothing for that, and then the positive side, and then there's nothing, and then there's positive, and then there's nothing, and you can see that in this diagram right here. The top part is half wave rectification. The negative part of the sine wave is not rectified. The positive part is. Full wave rectification, which is here, is this. This is where both parts of the sine wave are turned positive, and you get this triple pattern here rather than this kind of like 1.5 type of pattern. And this here shows you the diagram. The center part here shows the wiring diagram. This is exactly again, learn how to read this. Transformer, one diode does the rectifying. Transformer, 4 diodes operating as what's called a diode bridge. Often you'll hear the term bridge rectifier or diode bridge. That's what this is. This is full wave rectification. Okay. So once this rectified output is produced, it will also, as DC, it will still do this partial sine wave where it goes up and down, up and down, up and down. In order to smooth that, you will often see what's called a filter capacitor put across the circuit. It will try and flatten this line out, and I think I don't have the diagram here. I must not have put that in. So you'll often see a big filter capacitor, and those are those, on WPC boards, those are those big 15,000 radial snap-in capacitors, which some pinball vendors like to sell cap kits for. My advice to you is don't touch those capacitors. You will probably pull the through holes out. But those are the big fellows, they're the filter capacitors. The transformer secondary, the AC input, should always be fused. These diagrams here don't actually show the fusing because the fusing is done on the board. That's what this diagram shows here. This is the fuse for the AC input. An interesting caveat for those who are fascinated by the history is that Williams, in their early System 7 games, did not fuse the AC of their transformer output. If you do not fuse the AC and too much current flows through those wires, you will melt the insulation from the heat, and when the insulation melts, it will short, and when it shorts, too much current will flow, and it will start a fire, and if it starts a fire, your machine will probably burn down and you will not be happy. And this probably is what actually happened with some Williams machines, which is why they started fusing the AC side. If you have early Williams machines, System 7s, make sure that your AC side is fused, and if it isn't, put a fuse in there. Otherwise, you will start a fire if there is a short. Rectified output may also be fused, and this is useful for distribution. So if I have a 50-volt line for solenoids, and I decide to power three different groups of solenoids, if I individually fuse each group, one of those groups may draw excessive current, but not the other group, then that fuse will blow and it will tell you exactly which group has blown. And they do that really just to limit it. So rather than put a big 20-amp fuse that fuses 4 groups of solenoids, you can put 4 5-amp fuses and individually fuse that. And that's part of what you'll see is also done on some of these boards. Board consumption. Again, this is stuff I've actually just talked about. Digital logic, lamp matrix, general illumination. Off-board consumption is actually, sorry, I should go back. On-board consumption. On-board consumption is the power is rectified and then it is consumed directly on the board. Digital logic is where this happens. Off-board consumption is the power is rectified, solenoids, and is consumed off the board in the machine on the playfield. You will not have a solenoid on a board. There's no point for it. But this is just a differentiation of, again, following where the power goes, at what level. Typically, the higher voltages go off the board to power the solenoids. The lower voltages stay on the board for digital logic. So, and this final point here is about what I mentioned earlier about regulation. Regulation is used to provide a fixed voltage output level. So if I provide a regulator with 10 volts and its job is to regulate output at 5 volts, it will throw away half of that voltage. 10 volts, I don't need those 5 volts. I'm going to throw them out and I'm going to give you 5 volts based on the load that I have. Maybe, for argument's sake, the load of 1 amp. If we double the load to 2 amps, then the regulator still has to output 5 volts. And what it does is, instead of throwing out the 5 volts, it takes the 5 volts, delivers the 2 amps of current, and maintains the 5 volts. That's the job of the regulator. The job of the regulator is to keep the output at 5 volts no matter what the load. And you can see the same thing perhaps in a car, right? If you're climbing up a hill, you're putting a bigger load on the car. So what do? You make the engine work a little bit harder to maintain the same speed as you go up the hill. It's exactly the same thing here. You're forcing the regulator to work a little bit harder to produce the output that's required. So you may ask yourself, well, why do I care about whether the output's fixed? You know, I go up the hill at 50 miles an hour. If I slow down to 40, who cares? I'll just slow down. Well, the issue with regulation is that digital logic requires it. The definition of a logical one is 4.5, for argument's sake. If your voltage level falls below 4.5 to 4, then you no longer fall within the range of a logical 1. You're falling into what's called an indeterminate or an undefined level. And when that happens, well, it could be a logical 0, it could be a logical 1, but I don't know what it is. It's not defined. So the voltage regulator's job, no matter what the load, is to maintain that voltage at 5 so that logical 1 stays a logical 1 and its execution is determinate. Sometimes you'll see people talk about WPC resets, and that is when the regulator cannot keep up with that 5 volts. And by not being able to keep up with the 5 volts, the system says, well, I've reached the indeterminate level now. And once I enter indeterminate execution from a software standpoint, well, everything beyond that is indeterminate because I've just executed an unknown instruction. So what the system does, there's a watchdog in the system. It says, oh, your voltage fell below 4.5, reset. And that's the job, in that case, typically, and not always, there could be other things. The regulator hasn't necessarily failed. The regulator has failed to produce the 5-volt output, but the regulator itself may not have failed. You may not have given enough buffer to the regulator to be able to deliver the 5 volts. It's similar to driving up a hill, right? Perhaps you ran out of gas and the engine didn't run, and, well, it couldn't keep the same speed going up the hill. It's the same kind of principle. The regulator's job is to output a fixed voltage. And I'm running low on time, so I'm going to try and speed it up a little bit because I don't want to miss out on the bits at the end with troubleshooting. This is a wiring diagram. This is a bridge rectifier. This is the filter capacitor that I mentioned. This is the fuse. You see it's duplicated. All the circuits are always the same. There's always a fuse on the AC side. There's always a filter capacitor. Same thing here. This is the solenoid and the flasher side. This is individually fusing. On a WPC machine, there are 3 categories of solenoids: high pulse, low pulse, continuous duty, and they group them appropriately. And the game designer will assign the solenoids appropriately for something that needs a big kick, like a VUC, a vertical up kick. They'll typically assign it to a high pulse solenoid, a 50 volt to tip 36 drive, so they can get that extra bit of current to generate the stronger magnetic field to kick the ball vertically. Again, so this is how things are, circuit operation is how things are grouped. The manual has theory of operation, and I'm going to skip through this, unfortunately, because I know I'm going to be low on time. They typically group things together. Solenoids are grouped, as I've mentioned here, high current, low current, general purpose. Flashes are grouped together as dedicated or overlapped. The big issue that you'll often see on some machines is, like, for instance, Star Trek Next Generation or Terminator 2, is someone will say you need to do the tieback mod, and you'll ask yourself, well, what's the tieback mod? And the tieback mod deals with general purpose solenoids. I don't think I described it. Yeah, I've got a lot here and I'm not going to make it. So essentially, every solenoid requires a diode to stop the backflow of current. If the diode is not present, you'll typically destroy the drive transistor and from the collapsing magnetic field. And that's the tieback diode or the flyback diode. All diodes on Williams boards, WPC boards, all diodes on solenoids are located on the WPC board, not actually at the diode. And by virtue of doing this, they allow you to select it. So there is a wire that you can reconnect back to the board that will allow the diode to be put in circuit. And that's the wire for the tieback diode. And often that wire will either come out or fall off or do something from vibration. And when that comes off, there's no longer diode protection. And you'll always find on Williams machines, they're always part of the general purpose circuit. Because the general purpose one allows you to select a diode or not. The high current and low currents always have diodes. You cannot make a mistake with them. Okay. Voltage is matrix. Yeah, matrix is beyond action. So typically how things work in a machine from a power perspective is there's always power present. It's the path to ground that provides the power. So you should always be able to measure voltage at a point. So if someone often says, my solenoid's not firing, well, one thing they'll tell you is to measure the voltage at the solenoid. And the reason why is the voltage is always there. The solenoid energizes when the path to ground is provided. If there is no voltage at the solenoid, there can be no path to ground, and the solenoid will never energize. That's why it's really important to understand power is always present. And it's the same not just for solenoids. It's true for flashes. It's true for motors. It's everywhere. These machines operate on the power is always present to make things happen, provide the path to ground. And the path to ground is controlled by software, almost always. Not always in the case of special solenoids in System 7 and System 11, but it's almost always under software control. This is a wiring diagram of how the solenoids work, and I'll walk through this really briefly. Here's the rectification that you saw earlier with the fuse. This is the filter capacitor. This is the DC fuse for grouping. It goes out off the power board, down to your play field, goes through the solenoid winding, comes back through a different wire. Notice the colors are different. Comes back to the power board. And this here, this top part here is the path to ground. And it's kind of fancy, but essentially this transistor, this TIP36C here, acts as a switch. It's either on or it's off, and it's controlled by software purely digitally. You can actually bypass this by grounding the tab on the transistor that sometimes people will tell you to do that. You can't actually do it with the TIP36C. But for the purposes of I know that some have heard of it, some people have heard of it, you can actually ground that tab and you will bypass all of this control circuit. Essentially what you're doing is you're providing a path from this point where the connector is to ground, which is what the software does through this fancy circuit. Again, it's that same principle. Power is always present, path to ground is provided. In the case of an alligator clip, you're providing the path to ground. In the case of a game, the software is doing it. The reason why I want to hurry through this is that I want to leave some time for questions, because I'm running low on it. Okay, I think I actually discussed most of this, but there is something really important in this slide, part of the diagnostic process. So often you'll see people say, my solenoid doesn't work. Again, voltage power is required for operation. If voltage is absent at the solenoid, it is likely due to an interruption. That interruption can be a damaged component on the printed circuit board, the voltage is not being rectified, a blown fuse, deliberate interruption, or a broken wire, something has come off. If the voltage is present at the solenoid, but it's not present at the return, then it's likely to be an interruption in the return wire. That's pretty much it. If the voltage is present at the return, at the solenoid and at the return, then it's likely to be a problem with the actual software control. You can test that by grounding the tab of the TIP 102. The key to understand here is that software does that grounding. When you ground it with an alligator clip, you are bypassing software, and you are proving that the problem is in the software, not the hardware. Matrices are part of the next talk. They're way too complicated to talk about all this. The big thing with